To start the analysis, engineers draw a cross-section of the slope at a scale where 1 inch represents either 10 or 20 feet. They then draw a circular failure surface and divide the soil mass above it into 10 to 15 vertical slices. Each slice is carefully positioned so its base sits within just one soil layer, or where groundwater meets the failure circle. For each slice, the driving force is calculated using this formula. T equals W sub T times sin alpha, where T represents the tangential driving force, W sub T is the total weight of the slice, and alpha is the angle between the vertical and a line drawn from the circle's center to the midpoint of the slice's base. The resisting forces consist of three main components: the frictional resisting force, the cohesive resisting force, and water pressure acting on the surface of slope. Let's walk through how each of these is calculated. The frictional resisting force depends on whether there is water present in the slope. Without water, we calculate it using the total normal force, N against the slice base, which equals the total weight of the slice, Wt, multiplied by the cosine of the angle alpha. The frictional resistance is then determined by multiplying this normal force by the tangent of the soil's internal friction angle phi. However, when water is present, we must account for its effects. Water creates an uplift force that reduces the effective normal force acting on the slice base. The effective normal force N is then computed by subtracting this uplift force U times B from the total weight, multiplied by cosine alpha. The reduced frictional resistance is calculated by multiplying this effective normal force by tangent phi. For the cohesive resisting force, the calculation is more straightforward. It is simply the product of the soil's cohesion C and the length of the slice base L. This force remains constant regardless of the presence of water.